So, as we were doing it in the last class, decay of reverberant sound in a room, and if you recall, then what we are saying is, when I put off the with time, when I put off the steady sound some dB level, it is only I am talking of diffused sound, diffused field, right, and it will decay slowly something like this, asymptotically to the ambient level, asymptotically to the ambient level, right. So, it persists for some period of time, and if you remember, we said that at this point of time LP is equals to LW plus, just for the set of 10 log 4 by R plus Q by 4 pi R square. Yeah, this is what we remember, right. So, from there it will decay as soon as I put it off, this is not there, it will decay, and this decay persists for certain period of time, and it ambient, it reaches ambient asymptotically. So, it takes quite a bit of long time to come back to the ambient level, right. Now, this is important issue, this decay phenomena is important issue, which we call as reverberation, which I have mentioned earlier. Now, this is an important issue because some cases you might hear, if you are if you are if it is too long, if it persists for too long, then it might blur the direct sound. For example, you are sitting very close to me, then you get the direct sound straight away, but you will also get the reflected sound, diffused sound, multiple infinite reflected sound, and so on and so forth. Now, if this reflected sound persists for too long time, then it can create a little bit of interference with the direct sound itself. This happens especially with speech, because speech is, we speak in syllables, right, we speak in syllables, all right. For example, a long word like university, it has got university. So, supposing there is overlap with the last syllable and the last syllable from the direct sound, and reverberant field is coming and disturbing it, then there is a problem. So, it is discrete, speech is discrete. On the other hand, if you look at music, particularly orchestra or similar kind of lot of instruments and all that, since there is a rhythmic thing, it persistence give you a better feeling. So, instrumental sound, orchestra particularly of the kind of the Western classical type, Zubin Mehta, I do not know whether you have heard of him, is supposed to be a famous conductor, so such kind of some 100 violins, piano, and then so many things going on, and it actually the sound itself is of such a kind that you rather like that it should persist longer in your ear. So, while for music you would require to have good reverberation or it should remain there, for speech you would like that it should be within control. So, this is important, that is what I was saying. So, this is important, this issue is important actually. Therefore, we must find out some way to have a measure of the space, it should be it is the property of the space. So, some measure through which I can say, I can compare, at least distinguish one space from another in terms of its holding or persistence of sound. So, this is done in terms of reverberation time. Reverberation time, this is done in terms of what is called reverberation time, right. Now, reverberation time is defined as that time required for original sound to reduce to 1/1,000,000th of its value, that is what it is. So, if it was originally, so it is, that is mathematically of course is the power absorbed at the boundary, but once we would like to know, supposing initially intensity was I, say I initial, and then after certain period of time it reduces down to 10 to the minus 6 value of this, the time corresponding to this, time corresponding to this, time corresponding to this we call as reverberation time. The above, this we call as reverberation. So, this will we'll try to look at this now. Now, to understand this, we must look into rate of loss of energy in the diffused field and how it will be lost. Because supposing I have put off the source, now sound is absorbed in the boundary. Sound is absorbed in the boundary and nothing to replenish it. I am talking only of the diffused field. Remember, when I talked of earlier, I said that contribution to the diffused field comes after first reflection. Now, this will not be existing. Now, this will not be existing, because after it will not be existing after first reflection, nothing will come. So, there will be no sound coming to the reverberant field, because I have put it off, but sound will be lost from the boundaries. So, sound is absorbed in the diffused field, is absorbed at the boundary surface. That is what we have seen. So, this rate we want to find out, we want to find out this rate, we want to find out this rate. So, epsilon V, epsilon is energy density into volume of the room, and rate of change of this one, because it is reducing, there is a negative sign. You remember, V was given by C, at the surface, E is energy density into the volume, this energy, the rate of energy density absorbed will be this. Remember this formula, this is actually, what was this? This we said, this is the energy EC by 4 was this, the rate of change of energy. If I go back to earlier expressions, perhaps this will become clear. We said the energy density in the, if you recollect, we said that the amount of energy absorbed is equals to E C S alpha by 4. Remember this, we derived this formula. So, energy absorbed in all the surfaces will be given by epsilon C S alpha by 4, and that was equals to the energy coming into the field. W was the power source, 1 minus alpha bar is the energy coming after first reflection. So, this is the energy absorbed. So, this energy is absorbed in the field. So, energy at any state is epsilon into V. So, differential or rate of change of this one must be equals to whatever is absorbed on all the surfaces. So, following from here, then we go straight away there again back. So, this is the amount of energy absorbed in all the surfaces as we have derived earlier, and if I integrate it, I get d epsilon by dt, epsilon comes here, is given by this. So, epsilon at any time t, if I take from initial to some final state, right, E t is the final state or at any time t, and epsilon m is the original state, basically 0 to t time. I will get, if I integrate this, I will get it ln epsilon is equals to all this multiplied by t, and there is a minus sign here. So, E can be written in terms of exponential form, minus C s alpha by 4 b, C s alpha by 4 v comes here. So, this is what it is, and t was, after integration t would have come, there is a negative sign. So, epsilon initial and epsilon final, they can be related in this form of exponential form, and that is what I am saying. So, I said that E t by E 0, initial was E 0, at any time it is E t, that should become 10 to the power minus 6. That is what I was saying, that it should reduce to 1/millionth of its original value. So, E 0 is the original, and this is given, this was given, E t was given as E 0 into e to the power all that. So, this last expression, if you recollect, this was there, E t is equals to E 0 starting or 0 whatever it is, as it exists at the steady level. So, this is what it is. So, this time will then correspond to reverberation time, TR. I am defining reverberation time, which it will correspond to TR. So, ln 10 to the power 6, then I can write is equals to this, which will be 2.303 log 10 to the power minus 6, which will be minus 6 into 2303, because log of this is minus 6 into 2.303, because it was Neperian to natural log, I mean Neperian log to the base 10. So, this is what I get, and putting velocity as 340 meter per second, So, velocity I am putting as 340 meter per second divided by 4 and divided by 4, 4 and multiplied by this. So, 4 into 6 is 24 into 3 divided by 340 is 0.16. So, minus 6, this 4 goes here into 4 into 2.303 and the C I just divide. So, I get this divided by 340, this divided by 340, I get approximately is equal to 0.16. In other words, S alpha bar TR by V is equals to 0.16, 0.16 is equals to 0.16, right. So, I am writing this down. So, this this is simply, so TR then is equals to 0.61 by V alpha. From this it follows, because what I said was TR S alpha bar by V is equals to 0.16. So, TR is equals to 0.16 V divided by S alpha bar. So, this is expression for reverberation time. This is called Sabine's equation. This is called Sabine's equation. This is called Sabine's equation, right? Okay. Just this is so TR is equals to approximately 0.616 V by S alpha bar. V is the volume of the room, V is the volume of the room, right. So, this is reverberation time, equation for reverberation time. This is the simplest of all. There is more complicated ones, a little bit I will talk about them, right. Now, another aspect is defined, to look at it in some other form. This can be derived in another manner as well, but you can understand that it is it decreases, there is an exponential decrease, the curve that I showed. So, it decreases exponentially. So, this is dV, rate of change is equals to is a function of rate of change itself was a function of the time itself. Rate of change is a function of time itself. So, dV I mean not time, sorry, rate of time is a absorption itself. So, from this it follows that it actually, since it is, so it decreases exponentially, e to the power something negative as a function of time, e to the power minus some k into t. So, this form is a exponential decrease form, that is what it comes, right. So, let us look at it. There is a concept called mean free path. If n is the number of reflection per unit time and distance between average reflection I know. So, for n number of reflection, what is the travel time I can find out. So, for one reflection, what is the absorption? Epsilon diffused field multiplied by V, that is the energy density into volume into alpha. So, I am talking of reverberation. So, that is why epsilon r I have used here. That is the amount of energy absorbed in one reflection, and if I have n is the number of reflection, then total absorption in n reflection will be. So, total number of, if I know, if okay, let me remove this now, this is So, absorption per unit time would be epsilon r Cs into alpha bar by 4, that is what we have seen earlier, absorbed per unit time, and number of reflection. Therefore, I can talk in terms of, this is the energy absorbed in unit time. That is what we have got earlier, we have seen epsilon C divided S alpha bar by 4, right, and this is absorbed in one reflection. So, total number of reflection is given by this. Number of reflection, because number of reflection where per unit time or in 1 second will be given by this, because this is the energy absorbed in unit time, and absorbed in unit time, and in one reflection energy absorbed is this much, because epsilon r into V is the energy content in the whole volume multiplied by alpha. So, n is the number of reflection. So, n is the number of reflection. Therefore, one can get an expression for n equals to, see this n will be equals to, from this it follows 4 V alpha goes away, right, epsilon r goes away, I am left with C s by 4, B, Cs by 4B. So, number of reflection is equals to Cs by 4B, number of reflection is equals to Cs by 4B, right. So, mean free path is defined as the average distance travelled by sound between two successive reflection in the reverberant field. So, there will be an infinite number of reflections and their path length will be different, because in one case I am just drawing, see this is the source. So, the after first reflection it comes, and then this is the reverberant, let us say this is the in the reverberant field. So, this is distance travelled between two successive reflection. Next one it might travel much less distance depending upon angle of incident, and sometime it could be as like near vertical and so on. So, there are infinite, and sometime it goes back there, hits here. So, this is the distance between two reflection, and then it might take much longer path depending upon what is this angle. So, actually distance between two successive reflection varies. It will vary, it can be small as this, or can be larger depending upon what is the angle of incident, right. But average distance travelled by sound between two successive reflection I can talk about, right, average distance between two successive reflection, and that we call as mean free path, that we call as mean free path, right, that we call as mean free path. So, mean free path is equals to average distance travelled by sound between two successive reflections, right. So, can we now get some expression for this? Mean free path into n, that is number of reflection per unit time, must be equals to the velocity. Between two successive reflection it travels mean free path, and into number of reflection per unit time is the distance that will be covered in unit time. So, that is velocity. So, mean free path, this is equals to C, and number of reflections we have already calculated out to be Cs by V. So, mean free path is equals to 4B by S, mean free path is equals to 4B by S. So, mean free path is equals to 4B by, right. So, 4B by S. Okay. Energy in the diffuse field after n reflection therefore will be how much? Initially it was like this, after n reflection it will be, after first reflection it will be epsilon r v, right. What will be lost is this much, what will be left after first reflection is this. So, after second, so this is what after first reflection, which I can write like that, which I can write like epsilon r v 1 minus alpha. Now, this enters and then goes to a second reflection. So, what will be lost? This multiplied by alpha. What will be remaining in the field after second reflection? Epsilon r v 1 minus alpha into 1 minus alpha. So, that square basically to the power, right, and this I continue. So, if there are n reflection, after n reflection epsilon r v into 1 minus alpha bar to the power n, alpha bar to the power n, and right. So, after n reflection will be given by, in the diffused field after n reflection will be, from definition this must be equals to n into Tr if I define reverberation time. So, I am interested in reverberation time, deriving it in another manner. So, n T r, Tr is the reverberation time, into n is the number of reflection required for it to decay by 1/1,000,000th of a time. So, originally it was epsilon r v into 10 to the power minus 6. So, epsilon r v into 10 to the power minus 6 is the final, right. That must be equals to what has been lost in 1 minus alpha to the power n reflection, and n is equals to small into Tr, where n is the number of reflection per unit time, right. So, into Tr. So, that is how the definition is. So, I can get, you can see that I get an expression for Tr again in another manner, right, from this, because 10 to the power minus 6 into E r v must be equals to whatever has been lost in during Tr time, and in Tr time I have got n into Tr number of reflections, and each reflections after n reflections, that is what I get. So, that many number of reflection would have occurred during this period of time Tr, and after that the final sound that is there in the field is given by this. So, that must be equals to E r v into 10 to the power 6 by definition, because I am defining reverberation time as that reverberation time as that which will reduce it to 10 to the power 6. So, this is the expression. I take log of both sides. So, I get this will cancel out anyway. I am left with n t r 1 minus alpha bar equals to ln 10 to the power 6, which is 6 into 2.303, and then n we have already obtained as Cs by 4b, number of reflections in unit time. So, I just put in here and I get then 24203 C S ln 1 minus alpha bar. So, you can see this is how much is this? How much is this? Same 0.16 V, 24 by 2.303 in SI units, of course. It is because I am taking 340 meter per second. So, this is 0.16 V. So, TR is equals to V divided by ln 1 minus alpha bar. That's the derivations in slightly different way, and this is called Eyring's formula. Actually, this is Eyring's formula, but small value of alpha bar ln minus ln 1 minus alpha bar is equals to alpha bar. For small values of alpha bar, 1 minus alpha bar is equals to approximately equals to alpha bar. This you can prove, of course, from algebra. So, these two formula is same when alpha is small. Sabine's formula was the earlier one. Eyring's formula is slightly different. For small absorption, Sabine's formula is same as Eyring's formula. For example, if you look at it, 1 minus ln 0.9, ln 0.9, a negative value of ln 0.9 would be very close to 0.1, or you can express this as a series and you can see that approximated to alpha bar. That you can do for many, But there is something more than that actually. Both, if I use this formula, both assumes that my average absorption coefficient alpha, which means that by and large my absorption in all the surfaces should be of similar order, not too much of difference is there. Otherwise, there will be some more absorption in one corner, some less absorption in another corner. We are assuming all diffused field. Now, this formula can be extended actually for non-uniform absorption properties. So, Sabine formula also assumes that it is all absorption uniform diffused field. There are that kind of assumptions there, both of them. And if you extend this idea of different absorption in different surfaces, then you can extend the Sabine's formula in this manner. I am sorry, Eyring's formula in this manner. So, that gives us a way, assuming discrete reflections and taking the loss in every reflection rather than assuming a continuous decay. This gives us a way to actually extend that formula also. So, if you take this is the Sx, let us say x, y and z direction, I can consider 3. So, surface areas in this wall and the other wall, opposite wall, let us say that is Sx, and they are likely to have similar kind of absorption. Similarly, Sy is, let us say, the the floor and the ceiling, and Sz or Sz is, let us say, floor and the ceiling, Sy is the other direction, and their absorptions are likely to be similar, or average absorption I can take. Then I can get an expression for somewhat non-uniform absorption as well, assuming that average absorption between two opposite surfaces. So, 3 sets of them, I get an extended formula, right. So, that is what it is. So, where Sx, alpha x, etc., are the surface areas and average absorption coefficient in 3 orthogonal directions, right. So, it gives us a way to actually take account of that scenario also. However, we use this only for our purposes of auditorium design and similar sort of thing, but I think this idea is important. If your absorption coefficient are large and something you want to extend this, and there may be better ways. Actually, there are much better ways today, what is called image tracing actually. There are softwares which can do it. So, it would like the diagram, first diagram I showed, there is a point source and going in every direction. So, you can simulate this in a software and it is available. I mean, it's even you can write your own program, it is not a big deal. It can be just simply you can write it. So, this alpha x bar is the average absorption coefficient corresponding to two surfaces. Three orthogonal direction I have said, assuming it is a rectangular body by and large, I mean rectangular parallelepiped. So, in one orthogonal direction I have got two surface, other orthogonal direction I have got another two surface, and average absorption in these two surfaces, and average absorption in the other two surfaces, and average absorption in the other two surfaces and corresponding surface area. So, in three orthogonal direction I am taking the surfaces and there as the average absorption. Right, but then finally we use most of, we do not want to get into that kind of complicated, you can verify it, and it is possible to measure the reverberation time also. I am not sure whether I have a slide here or not, but just before I can just mention to you. See, what you can do is you can put a source at a given point. So, what is the source? It would be a microphone. Put a microphone somewhere there, right, within the space, room. Put a microphone. And then measure, it has to be of course the level meters, sound level meters which can track the sound and record it also. So, meter with recording the modern day instruments all are possible. So, what you do, you put it off, it's connected to a constant power source and a constant frequency, any frequency you want to test. Then measure the decay at one point, other points you can repeat it. So, time versus dB level at certain distance you measure with the sound level meter and recorder. So, you will find that it reduces in some manner like this, right, there will be and then you can find out, measure the time required to reduce it to by 1 millionth. How many dBs then? 60 dB, 60 dB. So, how much time it requires it to reduce to 60 dB by 60 dB, that is right. So, we will break and then again start. Thank you.